Hello students, so today we will be discussing about magnet resistance. Now this is actually the second version of the lecture previously posted. So you can find the first lecture in YouTube video number 42. The magnet resistance has been discussed. So this is actually the same thing, but in a more compact and more comprehensive format. Now, the magnetic resistance is the resistance, electrical resistance due to caused by the magnetic field. Now, whenever there is a flow of current or there is an electric field being applied along with the magnetic field, the electrons that are the reason for the conduction of any material, they tend to follow the helical path because of the crossed E and B effect. Due to this helical path, what happens is that the resistance, which is mainly due to scattering of electrons, uh, they they start to collide more because the circumference of the helical path is actually less than the mean free path. So this magnetic field makes the electron to collide little more. So that collision causes scattering of electrons, and that ultimately leads to an extra resistance imposed on the material, and that is called the magneto resistance. Now, the second aspect is what is the effect of temperature on this magneto resistance. If we decrease the temperature, we take a material called copper, which is the most common metal for electrical conduction, and we decrease the temperature. We take the temperature to 4 Kelvin, cryogenic scale. So what was observed that the scattering automatically got reduced because the collisions, the atomic movement or the atomic vibrations, they got reduced, and so this resistance actually decreased 10 times. So the temperature causes a decrease in magnetic resistance, and the materials which normally show this sort of magnetic resistance are a combination of a ferromagnetic and a non-magnetic material, like iron and chromium, cobalt and copper. So in this case, iron is magnetic, chromium is not. In the case of copper and cobalt system, cobalt is magnetic, copper is not. This was about the chemical composition. If someone tries to find out the structural composition of a magnetoresistive system, one can find three types of systems. The first one is the multi-layer formation. That when you create alternate ferromagnetic and non-magnetic material. The second one is a nanocomposite, where you have a base of a non-magnetic material, like here this is a silver, and on that base there are magnetic particles grown all over the place. So it's not any particular, you can say this is a magnetic particle placed here. Sorry. So there are different magnetic particles placed on. Initially, it's basically a cobalt matrix, a silver matrix, on which we have cobalt, which are ferromagnetic nanoparticles. So here all these magnetic particles will be placed like, sorry. Now the second one is, or the third one is actually rather a combination of the initial two structures. This is called the hybrid structure, where you have the antiferromagnetic material, formation of a layer of an antiferromagnetic material, and the nanocomposite material kept as layers. So this one is the nanocomposite material, this one, and this again is the antiferromagnetic material, nickel ferrite. Okay. Now, since it's about resistance, how to find out the resistance, how to quantify how much resistance has been developed due to magnetic field. So, for that, we need to find out the relative electrical resistance. So it's basically nothing but a ratio of the change in resistance before and after field divided by the resistance originally present. So it's RB minus R0 by R0. It's pretty simple. Now this resistance, if someone plots this resistance with the magnetic field, that means if we increase the magnetic field, what will happen to the resistance? So the answer is so from the plot you can see that the resistance actually goes down with magnetic field. Okay. Now this is mainly because of the fact that an increase in magnetic field, what it actually means is we are confining the helical paths. We are creating a smaller or a higher pitch, or the radius of the helical path or diameter of the helical path, they go down. So there is a diameter reduction and there is an pitch increase. So that actually causes a decrease in the relative electrical resistance. Now the second aspect is what happens. Now before that, let me discuss what is a giant magnetic resistance. So whatever we have discussed till now, it's called magnetic resistance. Giant magnetic resistance, when you have number of multi-layers kept one over the another, and you see the hysteresis, and of course this gives rise to application is in hard drives, but in giant magnetic resistance, the signature of the giant magnetic resistance is understood by the exchange bias. Exchange bias is when you find a shift in the image plot, then it indicates that somehow the electrons or the spins have been pinned here at the interface. So the spinning gives rise to an exchange bias. Now let's go into the effect of thickness of the ferromagnetic layer on the exchange bias. I think this is not T. Increase in thickness has been meant this value, the thickness of the ferromagnetic layer T. This is actually T. So it was found that the resistance increased up to a certain thickness and then it went down. So how can we explain this phenomenon? Now for that we need to look closely in the interface region. That means you have a ferromagnetic layer above, you have antiferromagnetic layer below, and there's an interface region. Now, even if the interface region is present where the spins are random, whenever a magnetic field is applied, so the spins which are close to the ferromagnetic region, they start to behave as if they are ferromagnetic. So the spins alongside the ferromagnetic region, they start to show ferromagnetic character. However, the ones which are close to the antiferromagnetic regions, the spins are aligned in the opposite direction to the ablation of magnetic field, as you can see, following the antiferromagnetic character. So at this stage, when there is a passage of electron through these systems, the scattering event which determines the resistance of the current, the scattering event is more for the ones which are bound opposite to the electron flow. So that is why, and this there is an increase in the relative resistance with respect to ferromagnetic thickness, because the lower ones which are opposite, which are causing scattering, they are the ones who are responsible for the relative resistance. Now this effect occurs up to a certain thickness. I mean, up to a certain thickness, like in the case of iron and chromium system, it was found that the effect of thickness, ferromagnetic layer thickness, was up to 7 nanometers. So with increase in thickness, the number of spins which are biased by the ferromagnetic layer above it, they increase. It may not be exactly, the orientation may not be exactly as a ferromagnetic material should be, but they are close to that. Okay. So there is an initial increase because the spin alignment, for the initial increase, it follows, or the percentage spin alignment, it follows the ferromagnetic region along the magnetic field. However, keeping on increasing the thickness, the effect of the lower antiferromagnetic spin orientations, they get more dominant. Also, they get less dominant, and that is why the relative resistance start to decrease. And a very most common example of this giant magnetic resistance is in data storage systems, that is the hard drives that is associated with the computer or the PC.